Hello everyone, this video is about lesson 9 of the Forces in Space scheme of work. This one's on unbalanced forces, and really it's building on what was done in the previous lesson. The diagrams look almost exactly the same, and all we're introducing is this idea that if the forces are unbalanced, then we have this overall force, or what we're going to call the resultant force, and therefore we get some sort of change in motion. Now at the moment we're not worrying about two dimensions, we're just keeping it really simple and thinking in one dimension. Later on in the scheme we get to two dimensions, but for now let's keep it really simple. So the example I'm going to use here is just really simple, and I'm going to draw this over on the left hand side of my page because I'm going to do some calculations down here on the right. I'm going to draw a car. So let's draw the car here, do my two trapeziums. It's like some sort of old American sedan, something like that. And the first thing I would do is just to get students thinking about the forces acting. Because one thing they might come up with, which would be totally legitimate, and a physics teacher pointed this out to me recently when I was thinking about this lesson, is, well, actually there's two forces that because we did this example in the previous lesson, there's two forces acting, one downwards, gravity, and then one upwards because of the reaction force. Actually, what we're going to do in this lesson is ignore those, and you'll have to explain this to students. Just say those aren't going to change. So the weight of the car, ignoring the fact that fuel is burnt, the weight of the car is going to stay approximately the same, therefore the reaction force is going to stay the same, so we don't need to worry too much. But let's imagine that actually this car is travelling in that direction, so I'm going to take that direction as positive. I might do that in red just to illustrate the difference. That's positive. That's something that we introduced last time. If you didn't introduce that in the last lesson, it's worth doing it now, that we always make sure we're clear what direction we're going to take as positive. So it's travelling that way, we're going to take that as positive. And let's say this is travelling at 2 meters per second, something like that. Now, what we want to introduce in this lesson is this idea. Well, there's two forces acting, and we're going to consider the two forces acting. Let's say in this example, when it's just speeding up, we've got a really big forward force. Now, it doesn't really matter what you call this forward force, either the thrust or the driving force. I'll just call it the thrust for now. There's a forward thrust, and let's say that's equal to 1,000 newtons, something like that. 1,000 newtons. That's going in that direction. Now, again, we're going to study drag forces in more detail in a later lesson, but I think that, they'll have some familiarity from Key Stage 2 with things like friction, and the idea of air resistance is quite intuitive. So we can talk about the backwards force as well, and you can elicit that, or just tell them that there's also a force acting backwards, which is a combination of friction and drag and so on. We'll just call it drag. It's one of the drag forces. Let's say there's this drag force, drag equals a 400 newtons. So if you've got a situation like this, where rather than the examples we saw in the last lesson, where the forces were balanced, in this case we've got an example where we've now got two forces that are unbalanced. What we can do is calculate the resultant force, or another way of saying the overall force acting. If you were to imagine all the forces and just reduce it down to one, this would be the force that's acting. So how do we work out this resultant force? Well, we looked at it in the last video, but it's even more relevant to this lesson. And this is where we are building the kind of habits that are going to prepare students to become A-level physicists or degree-level physicists, hopefully. And this is where we've got to be really particular about how we do this. So we've said it's travelling in that direction, so we're going to take that direction as positive. This is in that direction, it's in the same direction as our positive, so we're going to put plus 1,000, plus 1,000 newtons. Then we're going to take the next force, and we're going to see that that is going in the opposite direction. So we're going to take that as a negative. So that's going to be minus 400 newtons. So what's our resultant force here? 1000 minus 400 is plus 600 newtons, which means there's a resultant force in that direction of 600 newtons, like that. And what that means is, and we've not done anything particularly groundbreaking yet, but the link we want students to make, and again, this is building on that core concept that's been present in our scheme of work right the way from that lesson on the basketball and Aristotle and Galileo and so on. If we've got a resultant force, an overall force that way, that means the object is going to accelerate. So now we can really introduce that word and state what it means. Essentially, it means it's going to get faster. So that 2 meters per second is going to increase. So what we can do is then draw the kind of next part of the story. And you can see already this is building up to the kind of thing that we do when we teach students about terminal velocity. And again, that's why terminal velocity always comes up in exams, because it really gets students thinking in terms of these core concepts. So let's imagine the story a few seconds later. So here's our car again. It's gone a bit wonky, I'm not sure why. Here's our car again, and now the car is travelling at, let's say, or a bit longer. Let's say it's gone up to 8 meters per second. Again, I'm going to take this arrow as showing the positive direction. I'll just do it with a plus that time. Now let's draw the forces acting. Now let's imagine the driver has taken their foot off the gas a little bit, like that. But now, and again, we're not going to go into this in loads of detail because we're not thinking about drag force too much at this stage, but it's a fairly intuitive idea that the faster you go, the bigger the drag force. So let's say the drag force is now, drag is equal to 700 newtons, but this person's taken their foot off the gas, so the thrust is only equal to 300 newtons. And again, all we want to do is just model our resultant force calculation. So we're going to say resultant force equals, I'm going to go through the same thing. This direction is positive, so I'm going to do, well, that's in the same direction, so that must be plus 300. That's in the opposite direction to my positive, so that must be minus 700. Therefore, my resultant force is 300 minus 700, which is minus 400 newtons. So that means, if it's minus, that means my force must be acting in the opposite direction to this. So I've got a force in that direction. And it's a bit smaller than that one, so I might try and draw that arrow a bit shorter. Although my diagrams are definitely not to scale. Now what does that mean? Again, the Aristotelian picture here is that, well, the car must start moving backwards. That's not what happens. What we're going to say is, in this case, if the resultant force is that way, that means we're going to get deceleration. That means the motion is going to change, but in that direction. So in this case, we get a deceleration, which effectively does mean the car slows down. Now, again, don't worry too much. We're building up a very complicated picture. The main thing that we're modeling here is this process and making that link between resultant force and the change in motion. They're not going to get it all at once. So as long as you model it in a really precise way, and we keep doing that again and again, then hopefully they'll start to get the idea. Now, what we can do finally is tell the final part of our story. So let's imagine now we've got my car again. And in this case it's slowed down a bit because we saw it decelerated before. Let's say it's now at 6 meters per second. So that was still positive. It's now traveling at 6 meters per second. And because it's slowed down, I'm going to say the drag has reduced now, let's say to 500 newtons. And the driver has got the acceleration let's push the accelerator pedal down to the point where the thrust is also 500 newtons. So I'm going to put thrust equals 500 newtons and the drag equals 500 newtons. So you guys, I'm sure, can see what's going to happen here, but we're going to model it in exactly the same way because we're modeling a way of thinking, and we've got to be really, really structured about how we do that. So we're going to do the resultant force again. It's equal to, again, I've taken that as positive, so I'm going to say plus 500 for the thrust. The drag is in the opposite direction, but it's also 500. Because it's going that way, it's going to be negative 500 newtons. So I get a resultant force of 0 newtons. Now, again, this is potential for a massive misconception here. Students might think, well, if there's no resultant force, then it must have stopped. But you've got to point out to them where this fits within our story. We said it slowed down, but it was still going at 6 meters per second. So in this case, actually, if you've got balanced forces and therefore 0 resultant force, all that means is there's no change in motion. So I might put here no change in motion. That's the other side of our key concept, that if there's no resultant force, there's no change in motion. And then I'm going to introduce maybe some more language, constant speed. And again, we'll look at speed in more depth in later lessons, and as well as drag force and things like that. But really what I'm introducing here is just how to draw the force diagrams and how to calculate the resultant force. Again, it's all a bit chicken and egg. Like any scheme of work, you can't really understand one part of it until you see how it all fits together. So that's why we're going to keep bringing in lots of new ideas, but hopefully if we keep modeling this way of thinking, all the ideas will start to link up in students' minds. So that's basically all I would do. That is what I would model, those 3 diagrams, to show the kind of 3 different scenarios. What we're then asking students to do is do that, firstly with some really simple examples that they can do on whiteboard just with little dots, and just do simple resultant force calculations, and then state in which direction the resultant force is going, and therefore in which direction the object would accelerate or decelerate. And then in the second part, there's some kind of wordier examples where they have to draw the diagrams, label the forces, calculate the resultant force, and then again work out with what the change in motion of the object is going to be. But I think if you go through this process really, really clearly 3 times, and then get them to do some on whiteboards, you can be really, really confident that they're going to be ready to do some really high quality deliberate practice towards the end of the lesson. That's it for this video. In the next one, we will look at floating and sinking.